as Ulla already said nicely, I have been working with aerosols quite a while. We have moved on to some a little bit different topics now in TXRF, but I started in Dortmund in ESA, at the ESAs with under the tutelage of Reinhold Kloppenkemper and Alex von Bohlen. My PhD thesis was about aerosol analysis in Dortmund at that point, development of a method for impaction in different collections, just to make it suitable for TXRF. And I picked this up again, and when I moved to Loyola, I was in the meantime, I was working with René van Grieken in Belgium. We did also aerosols there, and the topic continued when I was doing my second postdoc at Princeton, where we did more a broader range of aerosols, not only for TXRF. So I did still TXRF analysis, but we did also some other methods, and this broadened my horizon. So you will see not only TXRF data, but also some other data. But then I picked it up in Chicago, and you can see here the skyline of Chicago. This is pretty much somewhere in summer or in spring. Today it's rainy and cloudy here. It's a typical March day, but the collections or the data or the research I'm speaking about is predominantly done in summer. Okay, so let me give you a little bit of an idea about the Chicago area. So just that you have a picture of why we are interested in studying aerosols in Chicago. You can pretty much study aerosols everywhere, but ultimately you want to have a hypothesis or some idea of why you want to do it, and also that you get some proper information out of it. So the Chicago metropolitan area is one of the largest population centers in North America. It has a roughly population of about 10 million. Chicago itself is about 3 million, and the metropolitan area is about 7 million. So it's a decent ratio. The metropolitan area stretches up to 200 kilometers and covers Chicago pretty much. Chicago is the third largest city in the United States after New York City and Los Angeles. It is one of the worldwide largest and most diversified economies, with an annual gross regional product of over 561 billion US dollars. And and just to put it in perspective, there are more than 400 major companies headquartered in Chicago, and some of them, 36 of them, are in the Fortune 500 listed, and 31 of them are in the S&P 500. So that tells you a little bit about the importance of Chicago as well. It has the largest commodity exchange worldwide. In fact, all the future grain, livestock, and gold prices are all traded in Chicago at the Chicago Mercantile Exchange. I understand this is now all online and not anymore on the floor. You can visit, if you are in Chicago, actually the Chicago Mercantile Exchange, as well like you can visit Wall Street. Chicago is the only US hub which has 6 of the 7 Class 1 railroads, and it has the most connected and second largest US port by value. This is O'Hare Airport. Keep in mind that ports are not only related to ships, but also to airports. So the O'Hare is the most connected ones in the United States and also has the largest value. And the US interstate with the largest or highest traffic volume is just south of the city. And this is squeezing right on the south shore of the lake. So there's the highest traffic volume and a lot of cargo going through. Moreover, Chicago is the third largest intermodal terminal distribution port globally after Hong Kong and Singapore. So there's a lot of freight going through Chicago and distributed throughout the American Midwest. Here you can get a visual picture of the actual area. So we have here the American Midwest. This is one of the areas. So we have the Northeast, the Southeast, then we have the Heartland and also the West. And often it is also fine. So basically it is more, you get a finer grain, and they talk not only the Midwest, but often the Great Lakes, which would be the states which bordering the Great Lakes, what you can see here as the blue blurbs. But the big area is actually the Midwest. And then when you look at the Chicago metropolitan area, it stretches for 3 states, Indiana, Illinois, and Wisconsin. Chicago is right here. And this is pretty much highlighted the area. And the one what you see here, this is Lake Michigan. So the main industries in the Chicago area are business and professional services. Kraft Food is headquartered in downtown Chicago. Transportation and logistics, United Airlines has its headquarters here. Many other companies have their headquarters as well. Manufacturing and healthcare, and also life sciences. Abbott Laboratories is here. Pfizer used to be in Chicago. So many of the big pharma and also food companies are actually located in Chicago, making it one of the most diversified cities. Geographically, as you could see, Chicago is in the Midwest of the United States at the southwestern edge of Lake Michigan. The Lake Michigan itself is the 5th largest lake on Earth by surface area, and is also the 2nd largest of the Great Lakes, also by surface area. The largest is Lake Superior, which is shared between Canada and the United States. And Lake Michigan is also the only lake which is completely within the United States. You can actually go across Lake Michigan. And it is the largest lake bordered by a single country. And when you put this in perspective, Lake Michigan is about the size of Austria. So you can imagine how large actually the lake is. When you are in Chicago, you can see the South Shore, but you cannot see across the lake to the east, because for us, the lake is east of Chicago. The climate, we talked a little bit about it before many of you joined, is generally continental. We have very hot summers here and very cold winters. So it's like in Kazakhstan, you can imagine that. And this is very typical for the American Midwest. Lake Michigan does play a role though, because it is a big lake, it's a big body of water, and in summer we have nice cooling time, and I will get back to this later because it has implications to our research. And in winter, unfortunately, you have lake effect snow. Now, luckily, that typically stretches out on the other side of the lake. So Michigan, which is east to Chicago, gets one of the most high snowfall amounts in the United States because of the lake. Not surprisingly, Chicago experiences regularly air pollution events, particularly in the summer. And this is the combination of the high traffic volumes, as you can see, local industries, and of stationary high pressure systems, which are typically associated with high solar activity, low wind, and warm temperatures. The Illinois Environmental Protection Agency, or Illinois EPA for short, monitors key pollutants between June and September, and at different stations, which are scattered throughout the Chicagoland region. And when there is a need for it, it calls it Air Pollution Action Days. And that means that people should take precautions in who have respiratory diseases or any other diseases. The EPA monitors only between June and September because at other times of the year, it's actually not necessary. So here you can see in a graph the traffic volume and also the major sources in the Chicago metropolitan area. You can see the red lines. These are the major interstates, which have predominantly interstates, some other streets as well, but they have very high traffic volume. And as the lines get thinner and lighter colored, there's less traffic volume. The dots and squares are local point sources, and the yellow star is where our sampling location, so where we took our air samples, is located. And you can see very clearly it's right next to the lake, but it's on the northeastern side of the city. And keep that in mind. I will show later another picture of this, which is a bit more, has a little bit more information, but it shows you that most of the sources of air pollution are actually to the west and to the south of the air pollution station. To the east is pretty much nothing, and to the north also not. Here we see O'Hare Airport, and there is another airport, Midway, which is closely in this area. It's not as visible on this particular slide as the other one. So the objective, why did we do this? The objective of the study was the identification of a specific air pollution pattern for Chicago, and is there actually something specific about Chicago? And then, of course, to design a protocol for measuring aerosols and trace gases to characterize this very specific air pollution pattern. So the air pollution pattern wasn't actually that difficult to figure that out, because one should not forget, as you saw on the previous slide, that Chicago is a coastal city. Lake Michigan shore is often considered as the third coast after the Pacific and the Atlantic coast. And because of this, and you saw Lake Michigan is really big, it experiences regularly lake breezes during the summer months. And this is due to the large temperature differences between the lake of the waters of Lake Michigan and the surrounding land. So let me quickly walk you through that. And it's easier done with basically a flow chart. So in summer, when the sun is up on the horizons, when in the morning, it's pretty hot here. And we know that the heat coefficient of land is lower than for water. So land warms up much faster than water in the morning hours. And when the land warms up faster, hot air rises. The hot air rises, and we have predominantly westerly winds in the Chicagoland area. And the warm air which rises is pushed across the lake, which is to the east of the city, in higher elevations. It cools down above the lake, and then once it's cooled down enough, it will eventually sink. It loses moisture and sinks, and then it moves back towards the shoreline, and eventually closing the loop by moving to the shore, warming up again, and so on. So you create this local cell. And it was found, so the surface of Lake Michigan is cold, and then you have the cold air sinking. It was found that lake breezes occur at about 20% of all the summer days. This is a rough average. It is typically formed in the mid to late morning hours and frequently between 10 and 11. You will see that we did a pilot study of figuring out when that actually happens. And in the early days of the summer, when the temperature difference between lake and land are the most extreme, because the lake can be is maybe like 10, 12 degrees Celsius, the land can be already 30 degrees Celsius. You establish a very intense cell and a tense temperature difference. The lake breeze can actually move up to 100 kilometers inland, and you can feel it. Once the summer progresses, the lake breeze will extend to a lesser degree. So it will, the lake water warms up, obviously, and the temperature differences are not as extreme anymore. And the lake breeze extends maybe 20, 30 kilometers inland, which is quite a bit as well. In the night, often the opposite pattern forms, which has implications to the air which resides above Lake Michigan. So in the night, the water is sometimes warmer than the lake, especially when it's coming later into the summer, and the air is basically residing above the lake. So the pollutants. One of the ideas was, or one of the hypotheses was, that the air which resides above the lake during the morning hours can undergo enhanced photochemical processing of the primary pollutants which were there initially present or which were blown out during the early parts of the lake breeze. Typically, the idea is, as I mentioned, when we have in the night the lake breeze, the land breeze, how you could call it, that the air pollutants which are above the lake will be stationary and nothing happens, so it's very quiet. And then we have the sun coming up and we have photochemical processing happening. And those pollutants, which are then first and secondary, but predominantly secondary pollutants, will be pushed back on land with the onset of the lake breeze. So the lake breeze will bring a push and a spike in air pollutants. The main primary pollutants are nitrogen dioxide and sulfur dioxide, which are common. And secondary pollutants will be ozone, nitrite, and sulfate. Both of them are more processed than NO2 and SO2. Trace elements, as we talking about TXRF, we also monitored obviously trace elements. And the question was, will they change or will they not change? Nobody has actually looked into this. And what we did is we designed a measurement protocol, which was designed to discriminate before the lake breeze and after the lake breeze. So, or while the lake breeze is in process. So before the lake breeze, meaning early in the morning time, and then when the lake breeze sets on, as I said, it was between 10 and 11 typically found, then we would start measuring around 11 or something like this and see whether we catch the lake breeze or not, or the onset of the lake breeze. And another reason why we did what we wanted to find out is, of course, to find the shortest time period possible to actually measure still sufficient data. And this was predominantly determined by the ion chromatography, by the ions, what we wanted to study. And for this, we did a pilot study in 2001, and that found that the lake breeze onset is most frequently between 10 and 11, as already said. and collection times should be at least 1 hour. We did measure initially with 2 different time settings, time increments, one for TXRF and one for ion, for elements and one for ions. But in order to compare the data, we summarized the 2 segments, or the segments which were for the TXRF or for the elements, and put them all together. We streamlined them, pretty much standardized them so that we can actually compare them. And you will see later, this is a 2 and a 3 hour protocol. 2 3-year studies were executed. The first were in the summers between 2002 and 2004. And the second, we did a follow-up. In the middle, we did a couple of other things in between those years, and so we did the follow-up studies between 2010 and 2012. The good thing about the follow-up study was that actually we could see whether there are changes in aerosol composition and also in concentrations. And it is quite interesting, and you will find that there are some interesting patterns which change over the years as well. So here one more time where the sampling location is. The blue part obviously is Lake Michigan. The downtown Chicago area is right here. The station is right next here, and here is the Chicago metropolitan area shown as pink to purple. Green are the there are farms or fields or open green, and then the blue lines are the rivers and streams which are in the area around Chicago, or going into most of them go actually into the Mississippi and not into the Lake Michigan. This is where an actually view from the location where we did the sampling. This is to the south. As you could see, we are north of downtown Chicago. What you see here are the L tracks, the elevated in Chicago. So there you can see actually an elevated going. This is downtown. That is the Willis or Sears Tower, as formerly known. And here are some residential area. It's mostly residential in our neighborhood. And the sampling was actually it's the tallest building on campus, which is about 60 meters high. And it's about 200 meters east from the lake. You can see here. So we have a southeast view, actually. This is part of our campus. You can see the chapel because Loyola is a Catholic institution. So we have, of course, a chapel as well. It's considered as one of the most beautiful, or the most beautiful churches in Chicago, because it's the only one which is right next to the lake. And the door actually opens towards the lake. And in the morning when there's sunrise, it's very nice to be there. And as you can see, the south and west, we expect most of the sources. So what did we measure? We measured aerosols, elemental and ionic species, as I already mentioned. We also collected or measured trace gases, ozone, nitrogen dioxide, and NO and NO2, so which are lumped together as NOx. And we also did meteorological measurements. So we had a small weather station which measured wind speed, wind direction, temperature, humidity, and pressure. So these are the 5 parameters which were important. If we don't have data, we did supplement them from local weather stations, which we can download relatively easily. Now everything is easily available over the internet and also quite validated. The aerosols were collected in 2 segments. As I mentioned, for the elements that were 4 actually, but we lumped those together in order to have the same grid. And so they were between 7 and 10 a.m. And this was, I labeled this as section or segment A. And then we did a break in between, and in order to let the lake breeze settle if it happens. And then we had a second segment between 11 and 1 p.m. And this was mostly done because in the morning we have less pollutants, whereas in the afternoon with the lake breeze, we expect more pollutants. The second segment was also called segment B. Trace gases and meteorology were measured continuously because this is just, you suck in the air and you get constant readings. The trace gases in a 1-minute resolution and the meteorology 5-minute resolution, which gives us a pretty decent picture of when the lake breeze actually does happen, because you can see the change in the wind direction, which I will elaborate on a bit later. The data, what I will focus on here today, are on the results of the year 2003 and 2011. And it would be just too much to use all of those data. But the reasons why we selected those two ones is because the days were roughly aligned with each other. So we started at the end of June measuring and went into early August, the first or second week of August, with a few interruptions. And because we cannot, of course, collect on days when it's raining, so it was only collected on days when it was sunny and dry. And so that limits the number of days. And moreover, we had data or sufficient data for both elements and ions. We did measure the trace gases continuously because there was no point of removing it and not doing it. But obviously, when you measure the elements, it's a little bit harder. This is our measurement station. So this is on the top of the building. What you can see now, this is a view to the west and where most of the sources are. On the right-hand side is the element collection. We had there some setup where we have open filter holders. There are 5. We had actually 4 segments, as I told you. And this for 2003 particularly. One of the filter holders was not connected to the pump because it was serving as a blank. All the other ones were switching on and off by solenoids. We have the flow meter, which measures the flow rate. And then we have the ion collection more measured here. We had a simple filter holder. I will show a picture on the next slide. And we sucked air through that and change the filter holder between the 2 measurement segments. This bucket here is holding our trace gases, which are going, the trace gas monitors are on the floor down. The same, the meteorology is somewhere also located here on the corner. So how did we sample? And I would like to point out there were 2 different types of sampling going on between the 2 years, mainly out of practical reasons and also time constraints. So in 2003, we did actually 2 separate collections, one for the elements and one for the ions. For 2011, we did 1 collection for both. And this has implications to also the sample preparation. And I will mention this where it is necessary. So in 2003, the elements were collected with an open phase filter holder, which held a 25 millimeter filter. And the filter had a pore size of 0.8 micron and was made of polycarbonate. As I mentioned, the blank was placed next to it, but no air was sucked through it. Ions were collected in this filter holder, which is roughly PM10. And it has 2 47 millimeter pre-cleaned quartz fiber filters back to back. This is a picture of the nuclear pore filter or the polycarbonate filter, which has little pores etched into it. So it's very thin membrane. Many of you know this. And this is an electron SEM picture of the quartz fiber filter. And fiber filters behave a little bit different because particles are collected on top of the polycarbonate filter, whereas in the fibers they will be collected within the filter. And this is why we did a back-to-back filter setup, because sometimes not everything is collected within the filter, but depending on the amount of particles and also the flow rate or the diffusivity of the material, it can break through and it's not getting collected. So we put a second filter back to it, and both filters were extracted and also analyzed, and then the data combined just to ensure that we actually collect all the data, get all the data and all the aerosols, what we have, all the elements and ions. In 2011, we used the same filter for both. So we collected with the same filter as for the ion collection in 23. And we used this for both, the data for both, for the elements and the ions, out of practical reasons, as I mentioned. It's mostly also time. So how were the samples prepared? For 2011, we had the same preparation for ions and elements alike, not exactly, but the first section. Whereas in 2003, we have, because we have 2 different sets of filters, we did start with we collected for the elements. So we basically digested the filters in a PTFE vessel. It's microwave assisted digested with 1 milliliter ultra pure concentrated nitric acid, and we added 100 ppb gallium as an internal standard. The samples were digested for 1 minute at 600 watt power. They were cooled down, and then we put it into microcentrifuge tubes. The digestion vessels were cleaned between each cycle, and they were also checked before the next filter samples to avoid memory effects. And then from the digested solution, we used 20 microliters and pipetted it on a clean siliconized quartz support, dried it, and analyzed it by TXRF. This is one of the very first instruments what Bruker, then they were still called Bruker, they were called Intax, sold, and this was called Picotax. By now I have a Picofox, but both data sets are actually still measured with the original instrument, the Picotax. And in this case, the measurement parameters were 1000 microampere and 40 kilovolt, and we used a molybdenum anode. In 2011, the same samples, as I mentioned, were collected and also analyzed for both ions and elements. For the aerosol, for the elemental analysis, a 1 milliliter aliquot was separated from the 5 milliliter master sample, which I will explain on the next slide for the ion chromatography, how it was used. And then we took from the 1 milliliter a 90 microliter aliquot and also added a standard to obtain the 100 ppb gallium as internal standard solution. Again, 20 microliter were pipetted and then the same analyzed as in 2003. So for the ions, which were done in both for 23 and 2011, and then for the elements in 2011, the initial setup was that the filters, so the quartz fiber filters, which collected all the species, were were put into in bottles, clean plastic bottles, in fact, and it was 5 milliliter of 18 mega ohm water, so ultra pure water was added. So keep in mind this is an aqueous extraction, not an acid extraction. The solution was then sonicated for about 20 minutes and then filtered in order to prevent that big particles are clogging specifically the column or produce particles or lumps on the TXRF support. And then we also did a regular filter on a blank filter, which we treated in the similar way. For 2011, as I mentioned before, 1 milliliter aliquot from those 5 milliliters was used for the TXRF analysis, and then from the master samples, from the remaining 4 microliter, 20 microliter aliquots, so 3 times, were analyzed by ion chromatography, and we used for anions and also for cations. And keeping in mind that for the trace gases, we didn't need to do anything because they just are measured in situ. So I just want to point out, because I will mention this later as well, but we did have in 2003 2 different types of sample preparation. And important to keep in mind is that one was an acid digestion, the other one was an aqueous extraction. For 2011, it was only an aqueous extraction, which gives us the opportunity to actually compare certain data sets. So what we did, so what are the results? In 2003, we have sampling days 15. We have, from those 15, there were actually quite a high number of lake breeze events, which were 7. This is roughly 47%. And the average temperature during the collection was 23.3 degrees Celsius. As I said, we started at 7 and ended roughly at 1 with an interruption of 1 hour. In 2011, we had more sampling days. The weather was just simply better. The number of lake breeze events was pretty much close to average, 5 out of those 24 days. So it was actually less than in 2003. And the average temperature during the collection was slightly higher with 24.6 degrees Celsius. So the next slide shows all the data combined. Let me walk you through that. So this is all the concentrations for 2003 and 2011. And the polar graph shows on the top, which is the northerly direction. So this is giving you the cardinal directions, north, east, south, and west. And in the center, this would be our measurement station. So when you are imagining yourself on the station, when you look to the north, you look up. If you turn to the right, you look east. And if you turn back, it's to the south, and to the left, it's to the west. The concentric circles you do see here are the concentrations, starting from very small in the center and moving out to higher concentrations. The dots are all the species combined. And what you do see is that most of the concentrations are in the center, so they're relatively small. And we have a prevalent southwesterly wind, so south and west, it's pretty much between those. And then we have also easterly winds commonly found, and northerly winds are not as common, and especially northeasterly wind. However, what is also noticeable is that the concentrations of any of the species is typically higher when the winds come from southerly directions, which I would, when we take basically half this sphere and go from east and west to the south. So the concentrations are substantially higher than to the north, which obviously is not a big surprise because most of the sources are to the north, to the south and the west. Now, in this case, what I did here is I separated the data points between 2011 and 2003. On the left-hand side, we have 2003, and on the right-hand side, on the bottom, 2011. Both of them are on the same scale, so go from 0 to 30,000 nanogram per cubic meter. And what you do see too is that this actually are quite different pictures. In 2003, we had very clear southwesterly directions, and almost none was coming from the north. Mostly southwest or westerly directions, very little northeast, northwest. Whereas the concentrations were high, reasonably high, when they came from the southwest and even from the southeast. If we move to 2011, the concentrations are much smaller, and it is much more well-rounded. So we have much more variable wind directions. There are still a few dominant southwesterly wind directions and also to the south in general, but there are many, many more data points which are to the north and to the northeast. So that you can see that there is a clear variation in differences. And that we saw actually higher concentrations in 2023 as opposed to 2011 follows pretty much the trends what the Illinois EPA also saw, the local authority. So they found that between, and this is a graph which shows the regional trends of different parameters between 1997 and 2017. The black dashed line is the gross domestic product. What you can see is increasing over those times substantially. The good thing, though, is that actually the pollution did decrease. Population did remain relatively steady, which is the dashed line, the green dashed line, and the vehicle miles traveled also remained reasonably steady. However, the solid lines show you that there were some spikes in the early 2000s, but by 2010, roughly, the concentrations, especially the haziest days, dropped all below 0%. So they decreased. And when you look at the arrow, so we were at 2003, which is roughly here, for the PM 2.5, which is a green line, it shows you that they were much higher than in 2011, which echoes pretty much the data what we found as well. So we are quite well in line with what everybody else found as well. So the data do look sound. So this graph shows you the major wind direction. So what we did is we discriminated between northerly, easterly, southerly, and westerly winds. Obviously, northerly, the predominant wind direction is north. Then we have east, south, and west. It's not often very difficult. It's sometimes difficult to actually say where we do the cutoff. So that's why we included also northeast and northwest, which is right between north and east, as in both as northerly and also as northeasterly and easterly, and also northwesterly and westerly winds. So they are lining up 2 times in this case. Whereas the ones which are predominantly north or south, they are, or east or west, they are showing up only once. So the percentages are shown to account for the different number of collection days. This is mostly done in order to get an idea of how can we categorize the pollutants with respect to cardinal wind directions. So can we say, is there a trend with respect to certain pollutants with certain wind directions? So there are, and you can see that the percentage of the major wind directions was quite different for the different years. And that obviously was already visible on the previous slides. So in 2011, we had predominantly northerly and easterly winds, much less southerly and westerly, whereas in 2003, it was mostly southerly and westerly, but much less northerly and easterly. It's just how the year is. And as I mentioned already, we need to keep in mind that all the sources are somewhat south, west, south, or west of the station. There's no source east of it, and very few to the north. This is Milwaukee, but Milwaukee is pretty far away. Well, it's not actually Milwaukee, it's Kenosha. This is pretty far away. So you can see here the darker one means higher pollution sources. There's O'Hare, then there are a couple of other places, Midway, and here we have a lot towards the southwest. So when we now go to the different segments, and this is for both ionic and elemental aerosols for segment A and B in 2003. Keep in mind, this is mostly predominantly southwesterly and southerly winds. And what you see is, and this is very interesting, so this is segment A, which is before the lake breeze or a potential lake breeze can kick in. This is not yet distinguished between a lake breeze day or a non-lake breeze day. It is all the days combined. So what you can see here is all in the morning, we have predominantly southwesterly winds, maybe a little bit northwest and southerly, but very, very rarely northerly or northeasterly winds. Whereas when we go to the second segment between 11 and 1, where we think the lake breeze kicks in, we will see that indeed, and keep in mind, and this year we had actually 50% of the days with a dedicated lake breeze, you can see that there is actually a change in wind direction and concentration as well. So here we have almost nothing from the east. Here we do have quite a substantial number of dots coming from the east. So ionic and so concentrations of elements and ions coming from the east. If we go to 2011, that looks completely different. There's a big scatter, and it accounts for, you saw that was only 20% of the days were lake breeze days. Moreover, it was much harder to discriminate because we had a lot of northerly winds, which is reflected here, a lot of dots towards the north and northeast. Concentrations are much smaller, they're much more scattered together, and they're much more all over the place than what we had in 2003 for segment A. For segment B, similarly, a little bit to a lesser degree. We still have a clear picture when we go to the easterly one, which shows us that there is a lake breeze. So we can say that here we have lake breezes, and here we obviously don't have lake breezes, and the red dots which don't show up here will be the ones, or red squares will be the ones which are associated with a lake breeze, those concentrations. So now let's go to the actual lake breeze pattern. What we wanted to do, obviously, is, are there differences with respect to ionic and elemental concentrations, and also nitrogen oxide and nitrogen dioxide and ozone? And I'm not going to show this here because this would be too much, but are there differences between a lake breeze and a non-lake breeze day? Can we actually use elements or ions to distinguish whether, or determine whether there's a lake breeze or non-lake breeze day, or as an indicator? And are there changes too? Because one should keep in mind that when the lake breeze sets on, we expected that there would be a spike of secondary pollutant, which can have major implications for public health as well. It's just a spike, but people who are sensitive and have respiratory disease might want to avoid days like this or times like this for being outside, because it can trigger asthma or other respiratory diseases. So what we did is we did have to obviously classify between lake breeze and reference days. So we decided that a lake breeze day is a day where the wind direction changed during the collection sequence from a non-easterly to an easterly direction. So for example, segment A experienced southwest winds or southerly winds, and segment B experiences southeasterly winds. So this is a 90-degree shift, roughly. And this can be from the west to the east, it can be from the southwest to the northeast, and so on. So anything which will go from a non-easterly, where there's no east, no E involved, to an easterly, where when on the segment B an east becomes an E becomes involved, would be considered as a lake breeze. In total, we measured 12 lake breeze days, 7 in 2003 and 5 in 2011. A reference day was a day where the wind direction remained steady for both collections. There were many days where the wind direction changed from southwest to west, from southwest to northwest, but that's not a lake breeze day. And it is very difficult to use this as a comparison for the lake breeze, because you would need to have a parameter which remains steady. So what we decided is there will be a reference day is a day where segment A and B experience exactly the same wind direction. Let's say southwest or westerly winds, or even easterly winds. If we start with a northeast wind and finish with a northeast wind, it will not be classified as a lake breeze day because there's no change in wind direction. Obviously, there were more reference days than lake breeze days in each collection year. 7, and in order to accommodate for this, we selected randomly 7 reference days for 2003 in order to match the 7 lake breeze days, and 5 for 2011 to match the 5 days in 2011. So we had a total number of 12 lake breeze days and 12 reference days, so for 24 days overall. What we did then, we took a t-test, a two-tailed t-test, applied that for selected species, both ions and elements, and in order to figure out whether there are indeed statistical differences between lake and reference days. And the species what we tested were nitrate, sulfate, iron, and zinc. Those were the ions, the 2 ions, and also the 2 elements were the only species which had actually sufficient data points to compare between lake breeze and reference days. We did not find on every day nitrate, sulfate, iron, and zinc, or any other species, for example, manganese or titanium also, were not found on every other day, but sporadically. Sometimes when we had southwest wind, we found a lot of pollution. When we had east winds, there was almost nothing. The t-test was applied to the mean of all the lake breeze and reference days. So basically, we took the data, we summed up the data for zinc, iron, and sulfate and nitrate for the entire collection sequence, so A and B, to get 1 data point per collection day. And then we split it in the 2 segments. The left-hand side, we have the entire lake breeze day, and on the right-hand side, we split it in segment A and B. So what we see here is that we can actually say that for sulfate and zinc, there was a significant difference between a lake breeze and a reference day. In sulfate, it's negative, and for zinc, it's positive. So you can see, and this is for the entire day. If we now take the segments, it is a little bit different because there's only a significance for sulfate for segment A. So there was only found that for the segment A, there was a difference between a lake breeze and a reference day. For all the other data points, it was not statistically significant to actually distinguish the data points between a lake breeze and a reference day. And this is sometimes necessary. It looks very close for some elements or for some species, but it is indeed not, because statistics is a neutral medium. Our eye and our perceptions are sometimes deceiving, and that's why it is important to do tests like this. And this is pretty much symbolized here, because when you look at the different, at this bar graph, where the red bars are the reference days and the blue bars are the lake breeze days for those 2 years, you can think that, for example, iron, I multiplied this by 10 because the concentrations for the sulfated nitrate was substantially higher. So, but when you look at this, you can think that the iron concentration, you would expect them different between a lake breeze and a reference day, but statistics tells us it's actually not. For nitrate, you can see there's actually no difference. Sulfate, it's clear there is a substantial bit difference. For zinc, it was found also significant. If we now go to the segments, you can see that there's actually, there are some differences for nitrate as well. For sulfate, we can see here the 2 ones, A and B, and the difference actually stands. As you can see, between A is here and B is not significant. For iron and zinc, it's, as you saw, it wasn't a difference, but we would perceive it potentially as a difference. So there are slight differences, but they are not significant. So the last thing what I want to talk about now is the comparison between ion chromatography and TXRF, because this study provided a unique opportunity to actually, validate the data, what we get with each method, to just compare them and see are we in the same ballpark? Are there differences or not? And the reason being is that 3 of the species, what we measured, were analyzed by both TXRF and eye chromatography in both years. Calcium, potassium, and sulfur were the ones. Whereas TXRF obviously measures the element, meaning calcium and potassium, and also sulfur, whereas eye chromatography measures the ionic concentrations, calcium 2+, potassium+, and sulfate. So I would also like to keep, and you need to keep in mind that these are 2 different methods, and we had also 2 different extraction methods. So for 2003, just to reiterate, the TXRF results were all for acid digested samples, whereas for the ion chromatography, they're aqueous extracts. This will mean that there most likely will be substantial differences because some of the species are not soluble in water. Calcium could be one of those, and sulfate can be another one. We didn't include iron because iron is obviously not soluble in water, not easily soluble. So and moreover, we didn't measure it with eye chromatography. For 2011, it's actually easier because the results were exactly from the same sample, and we would expect that there is a clear correlation. So these are the data for calcium in 2003 and 2011. We graphed the calcium ion is on the y-axis, the calcium element is on the x-axis. And what you see for 2003, which was somewhat also surprised, despite we had the acid digestion, we found that there is a decent correlation between calcium ion and calcium element. So the correlation coefficient is 0.845, and that is relatively good. For 2011, interestingly, where you would expect a correlation, there wasn't a correlation. Or I would say it's modest, it's not really significant, there's not much happening. And we found that, so that's a big question, and we think that there might have been something with the eye chromatography at this point of time. For potassium, it is the pictures all over the place, so we don't have correlation at all. For 2003, it's expected. For 2011, it is the same problem as we had for the calcium, because both are measured as cations, and so there might be some problem with the eye chromatography or with the column at this point of time. If we now turn to sulfur and sulfate, it is quite interesting. So in 2003, there is a slight correlation. It's not very significant, and you can see the data all over the place. Again, it's because we have 2 different sample preparation methods, but the good news are, and we were quite pleased with this data, in 2011, we graphed sulfur versus sulfate. So sulfate is here and sulfur is there, and we did find a very, very good correlation of 0.95. This is very good when you compare that those 2 methods are they are absolutely different. TXRF measures the element, it measures basically, it is spectrometric, whereas eye chromatography, it measures conductivity and it measures the ion. So it's pretty good. And the slope is 3.5. And the slope of 3.5 means that TXRF underestimates a little bit the sulfur concentrations, which is not a big surprise because sulfur is not necessarily the most suitable element for TXRF analysis. So in 2003, we found a slight correlation between calcium and calcium ion. The slope of 0.3 indicates that calcium is, that there is more elemental calcium than calcium ion in the samples, which is also expected because we have an acid digestion, which should extract more. So some of the aqueous digestion or extraction did not extract some of the calcium, which is bound, and so it's not extractable with water, so it's not water soluble. And but there is no correlation between potassium and potassium ion, and also sulfur and sulfate ion. So as I mentioned, we were quite pleased with the sulfur and sulfate ion correlation, but it was puzzling that we didn't find a correlation between potassium ion and calcium, because both we would expect that. However, we think that most likely something happened to the cation column, and there would be some variation. So we switched columns obviously between cations and anions, and since the anions are working and the cations not, we expect, we are a little bit surprised, and we hope that we figure out what's happening and do some additional data points if possible, but the samples most likely are not measured anymore. So it's not the TXRF in this case. And this concludes my presentation. I hope that you enjoyed it a little bit to get an idea about what is Chicago all about. And I would like to thank two of my graduate students, Tina Marie Fosco. She measured the 2003 data, it was part of her thesis, and Katrina Binaku. It was also part of her thesis. She did the 2011 iron data, and we had, of course, also a substantial number of undergraduate students involved, which helped with the collection, extraction, and analysis of the samples. And this just gives you a picture how it can be in winter in Chicago. And so I will stop sharing now, and I hope open the floor for questions.
Thank you. Thank you so much, Martina, for this very interesting talk. Let's see, maybe there are some virtual clappings. And also thank you to, showing us more on Chicago and the surroundings of Chicago. I think it's a wonderful city. I always love being there. And yes, now the talk is open for discussions. Are there questions?
I have a question.
Yes, please go ahead, Yoon.
At first, I'm not familiar with pico tags. So is this spectrometer with monochromatic X-rays or
yes, it is the same. It's a predecessor of the Pico Fox, so it's pretty much the same as a Pico Fox, just the initial version of it. So it has the same setup as a Pico Fox.
Molybdenum K-alpha is monochromatic. Yes. Oh, yeah. Okay. And my question is, are there any correlation between calcium and SO4?
I would need to look into this, but I believe there should be. So I think we did measure something, and there's so many data, but I definitely believe there were correlations. There was between calcium and sulfate, and I think between iron and sulfate there should be also correlations. I would expect that.
And are there any relation to the weather, or it's some rainy weather, or?
Yeah, when it was raining, we did not collect.
Mm-hmm. Thank you. Because I have experience from the aerosol particle from China. Mm-hmm. If the yellow sand has calcium, then always we found sulfate.
Yeah, that's to be expected because you have the calcium sulfate. And I did do this, and if I remember correctly, we did find this too, because there's a lot of calcium sulfate. We have a lot of cement industry and so on, so that would make sense.
Thank you.
Thank you. Are there more questions? Okay, so I have a question about the particle sizes. What are the mean diameters collected, and do you have information on the distribution of the particle sizes?
Not really. So we did do for the most of the total suspended matter. So for the ions, we probably have PM10, but the orifice is pretty big. So I tried to calculate this, and this was pretty big. So we didn't have size classification, and so you can expect pretty much a broad distribution. The cutoff for the small particles, it's a filter pore size for the elements. It was 0.8 micron. So everything what is smaller than 0.8 will most likely not be collected.
Okay.
We didn't have the time or the resources at that point to actually do size classification, but that's one thing what we probably will pick up at a certain point of time.
Yeah, because I expect that there will be elemental signatures depending on the size.
Yes, exactly.
I see Armin has raised a hand.
Yeah, hello, Martina.
Hi, Armin.
maybe I got lost at one point. So what happened with the sulfur and in the sulfate between 2003 and 2011? In 2003, the values were scattered as a no relationship between TXRF and ion chromatography, and in 2011 you had a nice linear relationship.
2003, you should keep in mind that we did two different extraction methods. So the TXRF samples were acid digested, where the sulfate samples were, so the sulfur was acid digested and the sulfate was water extracted. Whereas in 2011, both samples were, this was the same sample, literally. So we had actually two different samples, and that means in different methods. So I suspect what happens is that some of the sulfur is acid extracted and but not aqueous extracted. When it's sulfate, it's not necessarily all soluble in water, right?
Okay, thank you. And if there's time, I have a second question.
Yeah, sure.
Because now we have 2022. Is this project ongoing? Will you present new data soon?
It depends on availability of students. It would be interesting to actually pick this up after 20 years and see what's happening in this, but it's mostly a time question, whether I do have the time, and also resources, whether I have the resources, financial resources, and so on. Yes, I would love to continue this, but at this point, it's questionable.
Good, thank you, and good luck. Take care.
Thank you.
Yeah, thank you, Armin. Are there more questions? And then I have another question about the differences of the breeze days and the non-breeze days. There was a difference in zinc. And is there a hypothesis of where the zinc comes from? So it seems that there's more zinc when there is a lake breeze, but
let me just check. I think it is the other way around. I believe there was more zinc. No, actually, you're right. There's more zinc on a lake breeze day. And this is quite interesting because there's not a real theory. The only reason what I can imagine is because south of us in Indiana, which is southeast of us, there are some zinc smelters, and also in Michigan. And that could be something which could be brought in from the lake. So basically it could be transported across the lake. So we haven't done really source apportionment at this point of time, but it might be something to look into and have somebody look into this and do the source apportionment studies.
Yeah. And then the same question for the sulfate.
Sulfate is a processed pollutant. Keep that in mind. So all the sulfur dioxide, which is residing above Lake Michigan, will be processed in the morning hours and then come back as sulfate. So I would expect an increase in sulfate. I would have expected, though, also an increase in iron and so on with the onset of a lake breeze. But in fact, it didn't happen. So for sulfate and zinc, it is clear, but not for the other elements. Interestingly, nitrate is not. Despite nitrate is also a processed species.
Yeah.
Does that help you?
No, that I think, yeah, it's interesting to see how the weather changes the elemental content. Okay, are there more questions? Everything seems to be clear. Okay, if that's the case, then let's thank Martina again.
Thank you for having me.
Yeah, you're welcome.